Riemann tensor for a conformally related metric. So let's start with the first question, which is about modified covariant derivative. The covariant derivative in this problem, let's say mu alpha beta is equal to they're defining some modified covariant derivative, which is the usual Christoffel connection, the Levi-Civita connection, plus some tensor S mu alpha beta, such that well, Ashok says that this is completely antisymmetric once you lower this index, but we'll actually only need the fact that S mu alpha beta is equal to. Huh? Okay, I'll write it. Minus mu beta alpha, right? Let's say this much is true. Okay, and from here we'll go ahead. So the first part of the question is to show that let me use nabla instead of D, because I'll eventually end up using nabla because I'm used to nabla. So nabla tilde mu of G alpha beta is 0, right? This is the first thing to show, but let's try doing this. So nabla tilde mu of G alpha beta is really just, so remember that nabla acts using a partial derivative and then two gamma gammas, right? Here it will act with a gamma tilde and a gamma tilde. So now gamma tilde is just the difference between gamma and gamma tilde comes only in the gamma terms, in the S terms. So you'll just get two additional S terms, right? So this becomes what? This becomes del mu G alpha beta, and then it'll give you two S terms. What are the two S terms? It'll give you a minus S mu alpha gamma G gamma beta minus S gamma G alpha gamma beta. You understand what I did? Right? And this by assumption is antisymmetric, so this is zero. Right? Because in the question, if you remember, Ashoke also mentioned that G S say kappa alpha beta G mu kappa is antisymmetric. So that's 0. And second bit is the more computational bit, which is to show that d mu tilde, no, del mu tilde acting on a B, you want to define as R mu rho sigma. So here Ashok really defines this with a new mu. I usually define it like this. I mean, this is the usual conventional way to define R, and that's how he did it in class also. It's probably a typo in the assignment. The sigma T mu nu. I hope I do this correctly. I think sigma. I think this is how he defined it. Let me just make sure. Yeah. Right. So now the question is to find, R tilde. Find R tilde and T tilde in terms of R and the covariant derivatives, R and the usual covariant derivatives. So let's do this. So instead of taking the antisymmetric combination in the beginning itself, we really need to take this combination. Is this visible? I think it is. Okay, let's take this combination on a V rho. This is really what? This is just, let's do this derivative first. So that's just del mu acting on del nu tilde V rho. Okay, remember that the tilde nabla acts just like a nabla except for these S terms. So you have to get rid of these S terms. So let's get rid of the S terms. First, let me do it on the row. Okay, so on the row you have an additional S rho mu alpha del nu alpha V alpha. And then on a lower index, remember that covariant derivatives act with a minus sign. So minus S mu nu, say alpha del alpha tilde. Does it make sense? I mean, I'm doing this very quickly. I'm not going to partial derivatives and any gammas or anything, because that's not relevant to the problem. The problem is you can work at the level of the S's, right? That's what I'm doing here. I'm not going into the dels and so on. So if it confuses you, let me know. Yeah, so, and one more thing that I wanted to mention that many of you have missed in the assignment is that usually when you define a covariant derivative like we did in class, you could switch around the alpha and beta. You could define it as gamma alpha beta or gamma beta alpha. That is the same because the Levi-Civita connection is symmetric. This gamma is symmetric in the lower two indices, but it's not anymore because of the S. So if when you're defining a covariant derivative, if you're defining say del mu v rho, you have to be careful about whether you define it like this or whether you define it like this. Right? And these two are different definitions because this is no more symmetric. Okay? And this is the conventional definition, but you're free to use this. There's no really problem. There's no real problem. But I will use this definition, which is the conventional definition. Yeah, I don't know. Or. Okay. So let's do this more explicitly now. So this is a del mu, and I have to do the same business on the inner covariant derivative. So this just becomes a del nu v rho, and then comes with an additional S. That's an S nu alpha v alpha. That's the first term. Second term is S. Let me just write it as is. Okay. And the third term, I'll just write it as is. I don't want to write that thing down because as you can see, I want to express things in tildes, del tildes, and under anti-symmetrization, this is special. So I don't want to do anything there. So let's anti-symmetrize. Before anti-symmetrizing, let me just do one more simplification. So that's the first term. Second term becomes del mu S rho nu alpha v alpha and plus S rho nu alpha del v alpha beta v beta minus S alpha mu nu. Okay, so now let's anti-symmetrize. Anti-symmetrization of this, we already know, that's just remove. Oh, this is what I missed. Yeah. Oh, this one, right? This one. Yeah, thanks. Yeah, so this bit, we know how the anti-symmetrization of this works. That's the usual Riemann. Now, anti-symmetrization of this I already know, so let me just write it down here. The second line, that's just minus 2s. Let me write sigma mu nu. Okay, because S mu nu is anti-symmetric in the lower two indices, so I can just write that bit down. So now let me do the rest. The rest is what? The rest is, let me come here and do this bit first. So that's S rho mu alpha, S alpha nu beta minus S rho nu alpha, S alpha nu beta. Okay, so that's done. And I already wrote this one down. So now I have three terms left, this bit, and this bit. Okay, so let me write that down. Plus yeah, so V alpha and its anti-symmetrization. Next, this term Sum of this term, this one, right? Right. Yes. It will drop out when you antisymmetrize. Indeed. Yes, that was the argument. Yes. That's what I was looking for. Yes. So did you understand this argument? So this bit and this bit drops out because this, when you do a mu nu exchange, goes to that, and this, when you do a mu nu exchange, goes to that. So those two drop out. So I really only need to write this term. Right? And I missed a V beta. Okay, so then do you see the remote? Okay. So then you can directly read off R tilde and T tilde, right? So let me write this once more neatly. Is equal to R rho sigma mu nu, this term. Then let me write this term now. So that's a what? That's a plus del mu S rho nu sigma minus del nu S rho mu sigma. And then let me write this term plus S rho mu alpha S alpha mu sigma minus S rho mu alpha S alpha mu sigma. That whole thing times V sigma plus this term. And that tells you what T is and what R is, right? So this bit is just R tilde rho sigma mu nu. And this bit is T tilde sigma. Like a quick calculation, if you don't introduce partial derivatives, gammas, all of that stuff, you stay at the level where you want the answer at. Okay, so that's the first bit, first question. Now let me go on to the fourth question. Okay, second and third we will do. Fourth question is about trying to compute. So Riemann tensor, conformally related metric. Or Weil scale metric. Weil scaling is basically this phi coming out, which is what that means is just fancy name for this. So now the question is to compute the Riemann tensor of this. What I will do here is to first compute the Weil, this one. This is what that means. Weil scaling is this. It's called a Weil transformation. When you take a metric and multiply it by a function, it's called a Weil transformation. Okay, so let me compute the Riemann tensor of this. In order to compute the Riemann tensor of this, I'll just first compute the Christoffel. Okay, and the Christoffel I will show you has the exact same form as there. Okay, and notice also that in forming the R tilde here, I never use the antisymmetry properties of S. Okay, so the Christoffel I find here will not have the same properties as that S, but that doesn't matter because this R tilde doesn't need all those properties. So I can just directly write down an R tilde. Okay, let me do that. So what is Christoffel? Yeah, Christoffel. Christoffel tilde mu alpha beta. What's the formula? I mean, by now you should know the formula, so maybe others should tell. Okay, never mind. I'll write it down. I mean, this is something you should really remember when you're. I mean, you don't. Yeah, anyway. Right? Okay. So then, it's a bit inconvenient. So then gamma tilde mu alpha beta is just half. Remember that G upper is just inverse of G lower. So this gives you a phi inverse. And then G mu nu. And then you have to differentiate phi times G. So that will just be phi del alpha G mu beta with another term, which is just plus G mu beta del alpha phi. That's the first term here. Let me write the next few terms. Plus a phi del beta G mu alpha minus a phi del, sorry, mu G alpha beta. And then you have plus G nu alpha del beta phi minus G alpha beta del nu phi. You agree? Now, del alpha is just grad alpha because it's a scalar. So it becomes grad beta. Now I'll take the phi inverse inside. This phi goes away, that phi goes away, this phi goes away. And this becomes a ln phi. Because del alpha of ln phi is 1 by phi del alpha phi. So then you get a ln here. And so this is just, remember, note that the first term is just gamma, the old gamma. So this is just gamma mu alpha beta plus G mu nu G mu beta. Oh, sorry. Yeah, delta mu beta, indeed. So this gives you half delta mu beta del alpha ln phi, and the symmetrization of this, which is a delta mu alpha del beta ln phi. And then finally, you get a G mu nu G alpha beta del mu ln phi. And this is exactly in that form. So consider this as some, let me call it sigma, not S, because it doesn't really have the same symmetry properties, but I want to use this formula. So I will call this sigma mu alpha beta, which is explicitly written in only covariant derivatives. There are no partial derivatives, completely covariant. And you just put the sigma into that R and you're done. I mean, you can just leave it here, but if you want, you can put this there and cancel many, many different terms and write it neater, but this is effectively what it is. So yeah. Because of phi is a scalar, yeah, because phi is a scalar. So always remember that covariant derivatives act on tensors this way. So if you have a covariant derivative of mu, T alpha 1, alpha 2, all the way up to that, beta 1, beta 2. This is something you should never forget, which is del mu T alpha 1, alpha 2, and so, and beta 1, beta 2. Plus, you always get pluses on upper indices. So let's say you start with alpha 1, and then you get a mu differentiation index first. That's my convention. And then let's say you get gamma 1 times T, gamma 1, alpha 2, beta 1, beta 2, so on so. And you keep doing this for all n. Right? So that's a plus dot dot dot. And then you start with the minus signs, which is the lower indices. Right? So you get a mu, beta 1, gamma 1, T. Huh? That's a covariant derivatives act. So on scalars, since there's none of this terms, it's just a partial derivative. they commute for a scalar. Yes. But that's simple to see, right? Oh, another way to motivate this is, what is a covariant derivative? A covariant derivative that is anything if that takes in a tensor and gives out a tensor. If it takes in a PQ tensor, it gives you a PQ plus one tensor, right? So the covariant derivative is something that actually gives you a tensorial object. But the point to note is that del mu phi is already a tensorial object, right? If you coordinate transform this transforms like a tensor. So that motivates you to just simply define right here itself the covariant derivative is equal to partial derivative is correct. Now covariant derivatives commute on phi is simply the statement that this is del mu del nu. Oh well, it's not. But yeah, I mean this is an assumption. Sorry, this is the non-torsion assumption. Yeah. Yeah. This is the statement that the Christoffel connection is symmetric. Yeah.
For the modifier this connection in the first question, that statement will not be true anymore.
No.
Then there will be that.
Yeah. Yeah. Okay. Well, if we have more time, we can do more things.
Do you want to do it? Because I won't be doing. What do I need here? This I need. Oh shit! I needed this. Yeah. Maybe I should just not use this board. Where's the remote? Yeah, so I'll start with the second question first. So in the second question, we had the metric ds square is dr square over 1 minus kr square. So you were given this metric, and we were told that there's a transformation R going to F rho, which transforms the metric in such a way that it becomes some function 0. What was the, do you have the question? D rho square. minus rho square. Is this correct? Okay. Yeah, so this was the question. So we can take this and take this transformation and apply it to this metric. So dr will be f prime rho d rho, right? So dr square, so basically ds square will become f prime square d rho square divided by 1 minus k f square plus f square and this whole thing. Fine. Yes. Now we can compare these two to get an equation for f. So from here, the coefficient of d rho square gives us that g rho is equal to f prime rho squared over 1 minus k squared. And the coefficient of this whole thing basically gives us that this is also equal to f square, f rho square divided by rho square. So this is an equation of for f in terms of, this will give us like f in terms of rho. So okay, so let's take a square root of this equation. So we have f prime rho divided by square root of 1 minus kf square. Just give the equals plus minus f over rho. This is just df by d rho. So this just becomes df over f kf square. You just have to integrate this. Yeah. So one way to, I mean, there are many ways to integrate this. One way is to just take 1 minus kf squared to be some u. Then you have minus k f df, which is u du. You substitute that here. I mean, so the LHS of this equation just becomes integral. So df is u minus u divided by kf times du. So, and there's a f already here. So minus u du over kf square times, this is just u. And this kf square is essentially just 1 minus, wait, sorry. I want to take this as u square, this is not u. So it's just 1 minus u square. I mean, the 2 from here and here cancel. So yeah, this u and u also cancel. And so you have du over u square minus 1 basically, which you can do a partial fraction. So this is just, I think, half integral du over 1 over, what is it? Minus 1 over u plus 1. And this is just half log of 1 minus u over 1 plus u. Okay. And we know from this that u is less than 1. So that's why I've taken this sign inside log. So I would need. And RHS is just plus minus log of rho plus some constant which we can absorb. So let's say log of k rho. Let's not use k. Log of, let's say, a rho. Right. So equating this to this, we basically get square root of 1 minus u over 1 plus u is equal to plus minus a rho. Now you can square this. So you have 1 minus u over 1 plus u is a square rho square. And you can solve for u and you'll get 1 minus a square rho square c square. U was what? Yeah. What is f square here then? F square is 1 minus u square over square root k. This k. So if you substitute this value of u, so what is 1 minus of this thing? So 1 plus x square minus 1 minus x square will just give you like 4 a square rho square. And in the denominator, you'll have the square of this. So essentially, you'll get 4a square rho square over k. This is fine. I just substituted u from here. And then you just take the square root. So f rho becomes plus minus 2a rho over square root k. Yeah, sorry, a square. And 0, wait. Yeah, 0 was f rho square over rho square. So this is f rho square, just divided by rho square, so you get 4a square over k 1 plus. This is your answer. Okay, so third question. Actually, I should just erase everything. I'll just I have the expression, so I'll write it again. But yeah, these two expressions we'll be needing, so just take note of them. Question 3. So in question 3, we were given a tensor C mu rho sigma, which is defined this way. Yeah, so we're given this, and so we have to find the constants A and B such that for a metric of the form this tensor vanishes. Yeah. So this is what's called a conformally flat metric for phi positive. And from fourth question, we already know that if we compute the Christoffel symbols of like a metric G tilde mu nu, which is related to a metric G mu nu in this way, then the Christoffel symbols are related by something like this. The expression that was written earlier. Plus some other tensor, let's say S. And this S has some expression. And the thing that he just wrote down, basically, something. Let me just, and so this expression we had from question 4. Oh, I'm sorry. Oh, I was writing from your expression, and yeah, alpha beta. Yeah, I'll make these kinds of mistakes on board, so just correct me. Just don't look at your laptop. Just correct me when I'm doing something wrong. And from the first question, we know that if we have a Christoffel symbol of this form, then the Riemann tensor rho sigma. Okay, I shouldn't write this. Okay, so what I'm going to do is I'm going to make a substitution. This phi x is a little bit annoying, so I'll just write it as, let's say, some omega square x. So then this will get modified. It's the expression. Something like this. Yeah, and from the first question, we know that this is just this thing. This is the whole thing. Yeah, that's del mu s O mu sigma. Symmetry. That's half. Oh, sorry, not half. Two. This notation is probably not familiar, so I'll just write down. This was the thing. These two we derived in the first and fourth questions. So I won't do it again. But you can take this R and you can contract it to get the Ricci tensor and the Ricci scalar. And you'll see that like the expression, for example, for Ricci scalar is you'll see that for D greater than 1, both the Ricci tensor and the Ricci scalar don't vanish. So that's one thing that we would use. So for D greater than 1, R tilde is not equal to 0 and R tilde mu is not equal to 0 for arbitrary omegas. For some special cases omega may be, but not for arbitrary omegas. Yeah, so now what we can do is that we can take that expression for C and we can contract it with a G mu rho. And so G mu rho C. And this should be 0. Like for a metric of this kind. So and from that we'll get equations for A. Yeah, so if you contract it, G mu rho, the first term becomes this R nu sigma plus A. What does this term do? It becomes R nu sigma, right? Oh, R G. Oh, yeah. Oh, R G sigma. The last term becomes D times R nu sigma. So the last term is D. Let's say capital D is the dimension. R nu sigma. And plus. And the middle two terms are just R nu sigma. Because you contract with a G mu rho, it will give you a delta function and it becomes R nu sigma. So minus 2 R nu sigma. I guess this is correct. plus b times r. Now this, the first term becomes d times g nu sigma. Second term. So delta rho sigma g nu sigma. It seems correct. So we have let's collect the terms with r nu sigma and r separately. So we have 1 plus a times d minus 2. And here we don't have anything. Plus we have a. Yeah, we have a plus b times d minus 1. R. Well, I just said that you have the expression, and if you contract it, you'll get a messy function of in terms of omega, and that's not arbitrarily zero for arbitrary omegas. Yeah, but you have to write that expression. That's. Not any metric with R non-zero. Yeah. So if you contract it further, like the new sigma indices also, if you contract, so it's again zero. So yeah, I mean you can directly use this, but if you want, you can contract. It's this 1 plus a d minus 2. Plus b. Yeah, so this is I mean, since R is non-zero, you can solve this along with and substitute it back here, and you'll get a equals minus 1 over d minus 2. And 1 over. That's it, I guess. Fifth question, anyways, yeah. So black holes.
You can ask questions, we can discuss. But like if you say, tell us something about black holes. We should probably solve this like in a sense. I mean, once you solve that, it's clear what you have to do to answer your question. What in the second assignment?
How else would you find time?
No, it's not just the genetic equation. There's other things involved.
Some things.
And even solving the genetic equation, you need more things. Yeah, if there were more people, we could just solve for. There was some confusion yesterday about how many kilometers. written of this because we know that we C is called